You know, inside every single computer, from the phone in your pocket to the biggest supercomputer on the planet, there's a hidden speed limit. It's this fundamental traffic jam that means your processor, the brain of the whole machine, spends a shocking amount of its time just waiting. So today, we're going to dive into this problem, what they call the memory wall, and explore how the very blueprint of computing is being rewritten to finally tear it down. So to really get a handle on this, we have to start with a puzzle that, honestly, it seems to defy logic. Because if you just look at the raw speed numbers of the different parts inside your computer, you get a story that is super misleading. Okay, so check this out. On the left, you've got the bandwidth for PCIe Gen 5. That's the super fast connection for things like your SSD. It's clocking in at around 64 gigabytes per second. Pretty fast, right? But then on the right, you have standard system memory, your RAM, and it's running at about 51 gigabytes per second. So wait a minute, the pipe for storage can actually carry more data per second than the pipe for memory, which of course leads to a very logical question. Right? I mean, what's the deal? If the connection for our storage is this big, wide-open fire hose, why are we even bothering with a separate, seemingly smaller pipe for memory? Why not just have one massive, super fast connection for everything? Well, it turns out we've been looking at the wrong number. The answer, the real key to this whole puzzle, lies in the huge difference between moving a lot of data and moving data quickly. It's something called the latency trap, and it changes everything. All right, here's the best way to think about it. Bandwidth. That's like the number of lanes on a highway. More lanes are great, you can move more cars at once. But latency. Latency is how long it takes you to get on the highway in the first place. It's the time you're stuck at the on-ramp, just waiting to get going. And your CPU, it needs to ask for tiny little bits of data millions of times a second. So for the CPU, the time it takes to start the trip is way, way more important than how big the road is. And wow, when you look at the actual numbers, it's not even close. Getting data from your RAM takes about 50 to 80 nanoseconds. That's a super short wait at the on-ramp. But asking for data over that big, wide PCIe connection, even with all its bandwidth, it takes 500 to 1,000 nanoseconds. The wait time is just enormous in comparison. Yeah, we're talking a 10 to 20 times longer wait. Imagine asking a question and having to wait 20 seconds for an answer versus just 1 second. For a CPU that's doing billions of things every single second, that difference is an absolute eternity. And that massive gap is exactly why we've always had these two separate systems for memory and for storage. Okay, but this is where the story takes a really cool turn, because those strict walls that have defined our computers for literally decades, well, they're starting to crumble. New technologies are popping up that are starting to blur the lines between what we call memory and what we call storage. So the star of the show here is this thing called CXL, which stands for Compute Express Link. You can think of it as a really clever hack. It uses the same physical, high-bandwidth roads that PCI uses, but it adds a special express lane with a whole new set of rules, new protocols, that are designed specifically to cut down on that on-ramp waiting time. And its goal is, honestly, pretty ambitious. CXL's aiming to slash that 500 to 1,000 nanosecond wait time all the way down to under 200. Now, that's still not as fast as native RAM, not yet, but it's getting tantalizingly close. It's turning that massive 10 to 20 times gap into something more like 3 or 4 times. And what this really does is smooth everything out. Instead of these huge, steep cliffs between your CPU's cache, your RAM, and your storage, it's starting to look more like a series of gentle slopes. CXL memory carves out this perfect new spot right in the middle, bridging that giant performance canyon that used to exist. And this opens the door to something pretty radical. The idea of a single massive pool of data that can act as both super fast memory and long-term storage. But to really grasp why this is so revolutionary, we have to understand the historical problem it's trying to solve, the real villain of our story. Turns out this whole issue of keeping the brain separate from its memory isn't some new problem we just discovered. Nope. It's baked right into the very first blueprint for the modern computer, an idea called the von Neumann architecture. This one sentence just captures the problem perfectly. I mean, think about it. Since the 80s, our CPUs have gotten something like 1,000 times faster, but memory latency has only gotten about 10 times better. The processor has become this world-class sprinter that's just constantly waiting for the data to be handed to it. And this is what's known as the von Neumann bottleneck. See, the original idea was simple. You have the brain, the CPU, over here, and the memory over there. But that very separation creates a permanent highway between them. And as we've just seen, that highway is now the biggest traffic jam in all of computing, with data just being shuttled back and forth constantly. And you know what's crazy? This isn't just about speed. It's a full-blown energy crisis. Just look at this. The actual act of computing, of doing math, is incredibly efficient. But the act of simply moving that data from memory over to the processor, that can burn 10 to 100 times more energy. We are wasting incredible amounts of power just sitting in traffic. And that has huge consequences for everything from your phone's battery life to the insane cost of running these massive AI data centers. So the big question is, how do we fix this? How do we finally break free from a design that's almost 80 years old? Well, that brings us to the next, and maybe most exciting chapter in computing, where engineers are designing some truly radical new solutions. And some of the ideas on the table are just mind-blowing. You've got processing in memory, which puts tiny little calculators directly on the memory chips themselves. Then there's in-storage computing, which lets your SSD do some of the thinking on its own. 3D stacking literally stacks memory right on top of the processor for the shortest commute possible. And maybe the most futuristic of all, neuromorphic computing, which tries to build computers that work like the human brain, where memory and processing aren't really separate things at all. But you know what all these wild ideas have in common? It's actually a really simple, really elegant concept. Instead of always bringing the data to the calculator, you bring the calculator to the data. You just get rid of that costly commute entirely. So the very blueprint for computing, the one we've used for decades, is being torn up and rewritten right now as we speak. We're witnessing this fundamental shift away from a system that's been defined by its bottlenecks to one that's going to be defined by integration, which leads to the biggest question for the next era of technology: what comes next?